So, well, hello. I'm Dominic Hurley. I'm Head of International Relations here at the Institute. And today we're here for the Homi, Bhabha, Cockcroft, Walton lecture series, which is a series of bilateral exchanges between the Institute of Physics and the Indian Physical Association. Going a few years now, and all been very successful. Every other year, an Indian speaker will come to the UK, and then a UK speaker will go to India and give lectures on topics around sort of major global issues and how physics is helping address those issues. So today we're very lucky to have Mr. Rajesh, you're going to have to excuse me, Veeraraghvan, who is Technical Director of the Nuclear Power Corporation, which is a public sector enterprise under the Department of Atomic Energy. Rajesh has been a graduate of mechanical engineering and in the nuclear field for over 30 years. And today we'll be talking about energy transition in a carbon constrained world and how nuclear energy can help serve global in addressing challenges. But what's required for that will be obviously addressing public concerns around nuclear industry and also having a supportive government environment. It's interesting that those are two of the issues you've raised, because earlier this week the Institute published a report called Powering the Green Economy, Physics Powering the Green Economy. And we surveyed our members, and the survey came back and said 83% of our members don't think we'll hit 2050 net zero targets without considerably more investment in the relevant technologies and so forth. And also that 55% felt that public attitudes were a real obstacle restricting the technical advances in today. So no more from me. I'll pass over to you, Rajesh, if you'd like to speak. Thank you.
Thank you. Maybe I'll be comfortable by standing over there so that I can easily skip these slides or rather change the slides. It's thanks, Mr. Dominic, once again, and thanks to Miriam also. He's not there. He has been perfectly arranging this program. Like we in nuclear industry, and that's be perfect once we are working there. So she has been perfect in all my itineraries and other things. Thank you. Thanks for that. Today it's a great day. In what sense? In the sense it's a coincidence here. Like we have that COP28 happening in Dubai, where lot many heads of the states are there, and we have this equal topic to be discussed over here. There, of course, I think UK Prime Minister is there, King also is there, King Charles also is there, and Indian Prime Minister Modi also has gone, lot many other leaders. And every year they are, COP28, 27, 26, religiously they have been attending, and they have been giving lot many stress on improving the reduction of these emissions. That's what is happening. At least seriousness is coming or building up in the years together. But how far we are from the reality and what is reality? That requires an introspection. And what is required for this reality? That also has to be seen. One fact is there that overall, global temperature has been on rise. If you search on the internet, a lot of graphs are available. I have picked up just one graph from global warming index or something. And every year, the temperature has been rising. And it is, if nothing is being done, let us say, it will go up rapidly. And the thing which is attributed for this is simple, CO2 emissions they call. Or infrared rays, whatever is coming, it absorbs and it gives out. So that is a fundamental physics over this. So if you see, it is not just from fossil fuel electricity it is coming. This green is the power industry, which contributes to, let us say, and over to that transportation industry also is there. And over that buildings, once you construct, a lot of cement and other things are being used. There also it is there. The red one is industrial combustion, In India, I'm from India, we have one of the largest group, Tata Steel Group. I was told that around 40 gigawatt of energy they require. Out of the 3 gigawatt is only electrical. Rest 37 gigawatt is used for furnace heating and other heating appliances for making steel production. So one of the largest CO2 emitters is industry. Okay, any steel plant is having that many emissions. I may be wrong with the calculation. Tata Steel, I don't know. It is a hearsay for me. But in any steel industry or any other industry, a lot of furnaces are being burned, and in that fossil fuels are used. Then next we have industrial combustion. I told you. Then industrial processes are there where like mining. Mining is one of the important activity where CO2 emissions happen, and fuel exploitation obviously, and other sectors are very small. So altogether, power industry it contributes a good amount, and it has contributed equally. All these emissions are going up upon time, and this only is contributing for an increase in the temperature globally. But all these preambles are good, but there are universally, there are some disturbing facts in this. If you refer the statistics, but they are a reality. If you see GDP, gross domestic product, fantastic figures are there. If you see United States, you have the largest one always, and another developing country, China, it is next to that United States, and Japan, Germany, India is the ranking fifth. China and India are termed as developing countries, and others are developed countries. So we are also progressing well ahead, and many other countries are there. So if you see the GDP ranking, India may be standing fifth or something, and China is ranking second and all. But if you see the top CO2 emitting countries, United States obviously corresponding to GDP, but China again is there, and India is ranking way behind. It hardly gives 3.4%, whereas other countries are emitting 24.8 or something. So if you come to GDP per capita, you see there again, the developed country US is always per capita means divided by the population. Simple. It is near to about $80,000. It is there per capita. Whereas here you can see, because of this largest population over here, it is 2379 only. See, this much is there. So in the previous slide, you would have seen India's GDP was fifth in the world. But if you come to per capita, it is here. So this is the greatest disparity what we have in the universe. And this only is going to create problem in controlling the CO2 emissions. Why it is so? If you see power consumption, which I was telling, the greatest contributor for CO2 because of fossil fuels and other things, the per capita per person, how much kilowatt hour is being used. India is standing here, whereas the less populous countries are having good per capita per consumption, and where electricity is freely available, who have developed already, they are having large per capita per consumption. China is having around 6199 kilowatt hour per unit. We call kilowatt hour is per unit of electricity, and India is way behind, and other African nations are still way behind. Now, if you come to Human Development Index, and energy consumption per capita, this chart shows, like these countries are having the beautiful Human Development Index, and other developing countries, some China is here, and India is the green zone. This green zone is a very low quality of life, average quality of life, and very quality of life, very, very high quality of life. All countries obviously has to are aiming or are working to achieve at least this much. Obviously, there's no alternative. So here we are, and here China is there, and other developing countries are there. So to increase over here, lot of work has to be done by these green and red countries. And once we start working over this, obviously CO2 emission will come, because energy is a basic requirement. So, and on one side, CO2 should not be emitted, or CO2 emission should be controlled. And on the other side, each country have to grow up to reach this place. So how this imbalance is there, that has to be seen. Now, if you speak about carbon emissions, globally, if you see, so far in the period 1950 to 2011, United States, European Union, Japan, Russia, Eurasia, all these countries, developed countries have contributed this much, maybe of the order of 75%. And here, 25% is contributed by all these developing countries. So this is the global balance as on 2011, even 2020 also, if you see the chart, it will be like this one. So the issue is 79% of the historical carbon emissions are from this band, that is developed countries. You know, it is like today in COP28 summit also, there was a statement by different heads of the state that the problem is not by these developing countries, but solution has to be from the developing countries. There is no alternative. So all this band of yellow has to work very hard so that the total global warming is put under control. Now, how it can happen? That is a question today, because global warming is a common word, you know, common jargon or phrase nowadays. What is happening? And even some time back, my colleague was come, you know, our for photography, he was also mentioning about global warming. Okay, and each kid, you know, they are talking about global warming now. But how it can be controlled, nobody is aware. Means lot many ideas are coming, even from nuclear technology, small module reactor. So many philosophies are coming. I'll come to that now. Now, what is solution for this is all together have developing all these countries has to work together to have a cap on this CO2 emissions. Now there are different technologies available, you know, overall in the world, you know, for energy. So if you see, this is the chart showing how much is the life cycle emission. Life cycle means, let us say, coal means right from coal mining to burning of coal. Similarly, if you talk about nuclear here, right from uranium or mining to waste management. This is a full life cycle of each sectors of electricity is being shown here. So here, if you see, coal obviously is the largest. This is a statistics maybe in 2014. Of course, it will not change much now also. 820 grams CO2 per energy per unit of electricity produced from coal. It's coming. Then next come gas, then biomass, solar, which we call is a best alternative nowadays. It's also, you know, solar utilities and rooftop are in the range of 40s, and wind is the lowest as predicted as of now, and nuclear is next to wind only, right from uranium mining to usage in the power plants or elsewhere, and final product of electricity with radioactive waste management. The life cycle emission through nuclear is reasonably comparable with other renewable energies. So one of the best option what we are seeing is nuclear. So, but unfortunately, you know, nuclear is not has not grown to that extent what has been expected, except in some countries where you have 70%. In France, 70% consumption is from nuclear. Even in UK, it's hardly, now it is 6% or something. That's what I don't know the percentage, must be around that, or 6 gigawatt installed capacity is there. Some of the old plants they are phasing out. Germans have withdrawn from nuclear after that Fukushima. Again, they are thinking of reviving. Whatever is the case, if you see fossil fuels, you know, it is, or maybe the next slide would be, sorry. Fossil fuels is having this 436 gigawatt, and renewables are comparable, and nuclear is hardly 375. It is very much behind all these this thing. So if you see how to come out of this, that is a question now. Now, power sector, the earlier slide I showed, 40% of the global energy and industrial process. Power sector accounts for 40%, and industrial processes accounts for 60%. This is the combination. Means electricity accounts for 40% of the energy, and other sectors account for 60%. So both 60 and 40 has to be controlled for CO2 emissions. That means only power alone, if we replace all the power plants with, let us say, renewables and nuclear, that will contribute only to 40%. Whereas we have other sectors like transportation, energy consumption sectors, then even building construction and other things, industrial process, all those things account for 60%. So this 60% also, the input has to come from clean energy, so that overall a control is there. Now we have renewable sources of energy, which I was talking about. We have a hydropower, solar, which is quite common and it is expanding, especially in India, it is expanding like anything. Wind power, then geothermal and tidal, very minuscule, in the sense it is still upcoming. But you know, there are some difficulties with respect to all these bullets. Like this may require large RAN requirement, then low capacity utilization only is there. Means in the sense and seasonal intermittent sources. Like if you have a windmill over here, let us say it gives you 1 gigawatt. All seasons of a year you will not have wind. We have lot many wind farms in India also, but its average capacity factor is 30%. Sometimes it is 25%. Whereas if you compare thermal plants, it is 80%, coal plants, and nuclear plants, it is 90%. You know, like solar, when you have daylight, especially now in Britain, let us say you have 8 to evening 5 o'clock, you have sunlight. And if the temperature also is less, you will not have much energy produced to solar. Now, if you see how the strategy could be for replacement of or for addressing these energy needs, are we have to construct lot many new nuclear plants. Okay, me from nuclear sector, I have to advocate for this because of my experience in the past 33 years. I feel this is one of the best option available. And existing coal-based thermal plants, we have a new technology coming. I will touch upon that. That is SMRs, we call it, small modular reactors. And there are many captive power plants adjacent to any industry. Steel plants and other plants use captive plants. So those can be replaced by small modular reactors, or we have some new technology which is coming up known as micro reactors. MRs we call it. Now, why we go into nuclear power is, this chart can give a overall nutshell of the issue. If you have we are comparing 1000 megawatt hydro, 1000 megawatt nuclear, and 1000 megawatt coal fired. If you see the submergence here, it will go up to the level of 2000 to 5000 hectares. I'm talking about hectares. Of course, by kilometer, I don't know the value. This is the average. This much area is required. And it is obviously seasonal. Means once good monsoon is there, you have water, plenty of water. And if large monsoon is there, then more than power production, you will be releasing the water. And if there is no monsoon, then you are stuck again. So you have the load factor as 25 to 30% only. Whereas if you see the coal here, the land required is around, for the same 70 hectare land is required. And the fuel required is coal. As such, it is something like 3 crore 38 lakh rather. Can read it in billions or something. This much tons per year, that you can say 5 train loads of 2,000 ton each per day. We have a lot many wagons which will be moving, taking coal. It is a common feature what you see everywhere. And you have the emissions as 70 lakh ton per year CO2 is coming. All these emissions are coming from this coal fire. And you have an ash generation of 1.2 million tons. Whereas if you see a nuclear plant, land requires is very less, 20 hectares of land for the same 1000 megawatt nuclear. And fuel is 120 ton per year. 12 trucks only are required, very small trucks, things, and it will fuel for 1 year continuously. And there are no CO2 emissions as such. Okay, and the waste is very minimal, is less than 1 ton per year. So definitely you have a statistical advantage by seeing that comparing with another renewable best source of hydel as well as the recent coal-fired plants. So this was a statement given by Bill Gates some time back. He had penned a book, How to Avoid a Climate Disaster. Today in COP28, I saw an interview with Bill Gates that he is doubtful about meeting the net zero targets. That's what he has told today. But way back, this book came out in 2010, if I'm not wrong. I may be wrong also. So he has advocated for nuclear. So he has told that it's only carbon-free energy source that can reliably deliver power day and night throughout every season, almost anywhere on Earth. That has been proven to work on a large scale. Large scale is very important. No other clean energy source can come even close to what nuclear already provides today. So he has understood the reality over that. So one of the advantages with nuclear, as I told earlier, was low emission, and it acts as a base load power. Base load power means in the grid, like let us say grid requires some 2 gigawatt power, maximum 2 gigawatt power, and minimum maybe 1 gigawatt power. So you have to always pump in a constant amount of power. That is known as base load. So there are different types of stations, what we call base load station and peak load station. Base load is something you have to have a continuous energy in the grid, and peak load is whenever demand rises, you have to pump in more power. That is known as peak load. So nuclear is one of the best base load stations what we have seen so far. And in fact, the inclusion of nuclear power in the energy mix can help lower the cost of reaching the target of net zero emission, that an approach based only on renewables. Because renewable alone cannot help the scenery of reaching the net zero emission targets. Now nuclear power is stable. You can see upon time, like earlys in the earlys of 1977 in the left side graph, the capacity factor of greater than 90% was very less. That blue one, it was hardly 5% was giving that. Nowadays, upon time, because of improvement in technology and improvement in understanding of the nuclear plants, the capacity factor of more than 90% is very large. Almost 40% of the plants are operating the capacity factor more than 90%, which even thermal or gas-fired plants may not achieve. And in fact, the what you call high availability factor means the maintenance also is very down. In the sense, always it is available. More than 80%, many of the plants are available. This discussed. Now, if you see the total energy mix in the world, it is nucleus total generation, it is hardly 10% compared to the total thing. And obviously, gas and coal always is topping the list of it's around 60% topping, and nuclear is hardly 10%. So how we can increase that? It requires a lot of debate over this, because as Mr. Dominic was telling, we have to overcome the public perception in nuclear. That is the biggest challenge as on now. Even though we feel, after me working in the sector for around more than 30 years, it is one of the safest technology. If you are, and lot of inbuilt emergency systems or inbuilt fail-safe features are there, which always helps the plant running in a safe manner. But in spite of all these things, there are lot of public perceptions because of some stray incidents which has happened in the world. Now, if you see the projections, of course, this was done by IAEA, the International Atomic Energy Agency. In 2018, this total gigawatt was in the overall world was 7,188 gigawatt. Nuclear was hardly contributing 5.5% of that. And by 2050, the projections, if you simply go, if let us say if you are targeting for a net zero by something like that, nuclear can increase. There are two categories given: low and high. Low is something like there are old units which has to be retired after 30 years or 40 years of lifetime. As I understand, in UK also we have retired some good amount of gigawatt from that. But in India, we have another program known as Planned Life Extension Program, PLEX we call. So in that, what happens is after 30 years, plant's life assessment is taken, and lot many components are replaced in that, except for the main core and other steam generators and other things. Lot many components, pipelines and other things are replaced, so that it operates for another 30 years. We have planned Tarapur 1 and 2. It is the first boiling water reactor put in India, done by GE USA rather. And that plant, it started functioning way back in 70s, and it is still working. And last year we had taken a shutdown for again extending the life for another 20 years. So that technology we have mastered in India. So this, anyway, I've been preaching for nuclear, and these are the features and strength of nuclear. Now, coming to my country, that is India. India has given a net zero emission target by 2070. That is a commitment given by our leader. And another thing is, meet in 50% of India's cumulative electric power installed capacity from fossil fuels by 2030. These are the two great commitments what has been given by our government of India. And the lecture, Homi Bhabba lecture, what I'm giving today, he was the father of atomic energy. I will touch upon some part of India. Now, how we are placed in the nuclear energy. And he started the nuclear program. Homi Bhabba started the nuclear program in India. And this was a statement which is still valid today. Any substantial rise in the standard living in this region, that means he was knowing already that region is a developing region, that can be sustained in long term, will only be possible on the basis of very large import of fuel. That time fossil fuel, CO2 emissions were not known, it was way back in 50s, or on the basis of atomic energy. So atomic energy establishment was initiated by Dr. Homi Bhabha. And in India, this is the installed capacity mix in March 2023. That is 50% is through coal and lignite, pure fossil fuel. And nuclear is contributing hardly 2%. And solar is 16%, which is increasing. Then other renewables are also there. So likely installed capacity, you see the right side table, or by 29-30, you see there is a large increase in megawatt, or it is something like 77 gigawatt will be 777 gigawatt has to be installed all India by 2030. In that, nuclear is about to reach around 15 gigawatt. That means presently we have around 7.2 or something. It will have to have a 100% jump in another 5 years time, and we are working towards that. If you see, we are going to meet the earlier commitment of India, that is meet 50% of India's cumulative electric power installed capacity from fossil fuel source by 2030. So here we are working for installing hydro plants, small hydro, pump storage plants. Means pump storage plants is something like you release water in the hydro plants, and when you have less load, you pump back that energy, pump back that water back to the dam, so that can be further utilized. Then wind, biomass, nuclear. So coal and lignite and gas, who are the basic fossil fuel, will be hardly contributing 35%. Means 70% will be coming from clean energy by 2030. This is the target made in India. Same. Now, if you see the starting of nuclear program, it started way back in 40s through an establishment of Atomic Energy Commission in 1948, and lot many institutes for catering the whole ambit of nuclear program is there in India. We have Indian Rare Earths Limited, Department of Atomic Energy, under which IRA also has come now. Then Uranium Corporation of India is there, who is doing the mining. Nuclear fuel complex is there, who process the UO2 and they give us fuels. Heavy water, we are based on more pressurized heavy water reactors, PSW as we call, that also is there. Then we have advanced technology centers. Then in 80s, we have established Indira Gandhi Center for Atomic Research, we call IGCAR. That is basically concentrating on fast breeder reactors, which is a promising technology, and we are already constructing a prototype fast breeder reactor using plutonium fuel. So under this Department of Atomic Energy, we have R&D centers are there. Then public sector undertakings, in which I belong to, Nuclear Power Corporation of India Limited. Then lot many industrial organizations are there, Heavy Water Board, then Nuclear Fuel Complex, then Board of Radiation and Isotope Technology, then service organizations which help us all. And there are some research institutions and aided institutions. All these things put together, it is a very large organization of Department of Atomic Energy, which was envisaged or which was formed by Dr. Bhabha. So this is a 3-stage indigenous program, which was envisioned by Bhabha and which we are continuing now. In the first phase, we have PSWR, that is pressurized heavy water reactor we call. And in the second stage, we have FBR, that is fast breeder reactors. And in the stage 3, it is yet to be in action, that is using thorium. So here, in PSWR, we use natural uranium. Natural uranium is simply what is available in the nature as an ore. You take up, process that and put it. In that, we have U-235, uranium-235, isotope uranium. Then U-238 and U-233 and other small elements are there. So all these things put together, we have natural PSWRs, and from this uranium-238, we get plutonium-239 we get. And that plutonium-239 is being used in the fast breeder reactor. And along with that, we add one, we have lot many deposits of thorium, in India. Monazite sands are there available in beaches of Kerala and other parts. So there we have thorium-232. So we put a thorium blanket in the fast breeder reactor. And with that, we get uranium-233, which is again a fissile material, which can be used for further in the third stage. So this first stage, we have mastered the technology around 10 gigawatt, 7.2 gigawatt, 7 gigawatt around we have there. And fast breeder reactor, we are constructing a new plant. And thorium, it is in the experimental scale. So we have some more light water reactors, which has mainly come from Russia now. They are using light water reactors of VVER technology. This is a 1000 megawatt reactor. We have already 2000 megawatt reactors in operation, and another 4 more reactors which are under construction. So my company, Nuclear Power Corporation of India Limited, it is having all facets of business in the nuclear field, nuclear power project, right from design, construction, commissioning, operation, maintenance, waste management. Then we do plant life extension using renovation modernization, upgrades we do, then plant life extension, and obviously quality is the supreme in this. And we have expertise in PSWRs we call, and in all capacities, 220 megawatt, 540 megawatt, and 700 megawatt electrical. Boiling water reactors we have, and pressurized water reactors we have. We have all 3 types of reactors here, and we have an excellent safety and performance record. Nowhere you would have heard that something has happened in nuclear plant in India. We, like UK also, we are a responsible country in that. And assets, we have 17.34 billion assets, and our company's net worth is 6.3 billion. And we have a large expansion plans, like I was telling earlier, that we have 100% increase in the capacity will be there in years to come. Now, this is the thing. We have 23 reactors as of now in operation. 7.4 gigawatt production is there. And in that, 19 are pressurized heavy water, and 2 are boiling water reactors, and 2 pressurized water reactors. Multiple technologies are there with us. And under construction, another 7.5 gigawatt is there. 9 reactors are under construction. And there are 5 PSWRs and 4 light water reactors. Then we have another ambitious plan of another 10 reactors PSWR of totaling 7 gigawatt in the near future. Maybe that also may come up in another 5-6 years time. So altogether, if you see by 2031, 32, that means maybe some 8 years from now, we will have an installed capacity of 22 gigawatt as compared to the 7.4 gigawatt as of now. That means a 3-fold increase is planned. So our country is moving fast in establishing these nuclear plants. So these are the reactors in operation where we have 7.4 gigawatt. That is, first reactor was Tarapur 1-2, then Tarapur 3-4 is there. Then we have Kalpakam, we call Madras. Earlier it was Madras, now it is Chennai. Then we have Narora. Then this is 1000 megawatt reactor. And we have 4 units here of 700 megawatts known as Kakrapar in Gujarat. We have in Kaiga near to Goa. And we have in Rajasthan. Around 8 units are there. So reactors under construction are Kakrapar, we call it. And another is in Rajasthan, we have 2 units under construction. In Haryana, the northern part of the country, we have 2 units. Then in Kodangulam, we have 4 units under construction. This is the southernmost part of India. It is there. One of the biggest challenges in this nuclear industry is human resource. So you should have qualified and licensed human resources for operating these reactors safely, designing these reactors safely, and other things. So we have one Homi Bhabha National Institute, which is established in Mumbai. And other than that, we have different training centers at different areas in the country. And overall, we have many postgraduate and doctorate programs available. And intake of around 500 engineers are there every year. Every year we take 500 engineers without fail. Average I'm talking about. 500 engineers and scientists are being taken. And they are trained for 1 year. Rigorously undergo through rigorous training in different training schools and in plant training and other things. And they are being put in the plant design and construction and in the research area also. So nuclear technology, if you see, in India, we started a technology demonstration plant with, of course, Canadian help in the 1970s. Further to that, it is totally indigenized from 1980s onwards. No foreign help is there. And This plant, all 220 megawatt was there up to this area. And further we started 540 megawatt. And now it has reached 700 megawatt. We have mastered all these three technologies. So one of the important aspect in nuclear plant where public perception is there that it may prove harmful to the thing is, the one of the thing is you have to contain the any accident release of radioactivity in case if something is there. So if you see how the containment has evolved, containment is something like this. Outside what you are seeing, any reactor, it will be like this. Container is like that. So earlier it was single structure. Now further to that, partial double containment started, and further to that, pre-stress containment started, and further now it is standardized that it will be have a double containment. So this is one of the safest designs. If you see, you have double contained and inside one liner also. So any accidental release of reactivity, if at all happens, it may not happen, that is separate. If at all happens, will be contained inside this zone. And now all the reactors here will have this design. Means we have double containment with pre-stressed inner containment steel liner and RCC reinforced cement concrete outer containment. Now other safety systems in this pressurized heavy water scheme is, this is one of the safest reactor design in the world. Why so? The core damage frequency is, it is something of the order of what you call 4.17 10 to the power -8. You cannot say 0. So you have to assign some value based upon analysis. So reactor per year. So this is the core damage frequency. It is one of the best in the world. So there are certain features which are inbuilt in this. See, one is double containment, which I told. Another is we have 2 parallel shutdown systems. Like if one fails, another one will act. So one will not fail, but as a backup, you have one more thing. In nuclear, everything you have backup. That is one of the most important aspect in nuclear. So we have emergency core cooled system in addition to normal cooling system. If that fails, you have an emergency core cooling system. We have a containment spray system. Containment spray in the sense, if at all, if some line ruptures inside the containment, reactor will stop functioning. But whatever steam mixture, gas mixture, all these things which is happening in the containment, through a spray, to control that pressure over there so that nothing comes out. We have passive heat removal system. This is one of the finest designs. But of course, in all the reactor technologies, latest technology you have, in the sense, without passive means without aid of any external power. Everything due to natural convection here it happens. No, it is like you have some heat exchangers kept on the top of the building, and if all power supplies are going, then also because of hot water going up and cold water coming up, this will work out. Then we have primary containment control discharge. Then secondary, even the containment also there are some safety systems, and there are some filtered venting systems, and passive auto catalytic recovery. This Fukushima accident is there, which is the latest one which we have seen in the what you call television and all. Fukushima, you would have heard, Japan. There, that something like an explosion happened. It is basically a hydrogen explosion. It is not a radioactive explosion, because if a metal means there are zirconium and other metals are there. Metal and water, if it reacts, hydrogen will be produced. And if hydrogen comes into a concentration level, and if some temperature is there, it will blast. So that is a hydrogen blast. So we have some passive auto catalytic recovery made of some palladium or something. So you pass you device in such a design in such a way that this hydrogen goes through that, it will get itself converted to water. So hydrogen dioxide will convert to water, so that hydrogen concentration is avoided. Then we have hookup station, in the sense if all the power supplies are going and because of some reason, some tsunami or some earthquake or something, all the power supplies are going and there is nothing. We have some diesel driven truck mounted devices which will be stationed elsewhere, and from inside of the plant we have taken certain pipelines and cables and other things which can be connected on war footing basis. This device also is there. And for that, we have air-cooled DC generators. And overall, we have on-site emergency support center. This has been designed in such a thing like any seismic activity, it will withstand. And so only some what you call core important parameters will be monitored here. This is in addition to the control room here. if control room becomes inaccessible, then this will be available at all point of time. So these many safety features are there with respect to any nuclear plant, and this is there in almost all the plants which are being built in the world. So this is how a nuclear reactor of PHWR will look like. This is the core of the reactor, and it is heavy. It is using natural uranium. So natural uranium will not get a what you call chain reaction if water is used, because water will absorb lot many neutrons. So we use heavy water, and heavy water we have sufficient indigenous capacity, and here we have pressure tubes. So water goes through here, and anyway the full cycle is not there. This is the core of the reactor, and this is the fuel what we use inside these reactors. So these are the three technologies where we have mastered. This is known as pressurized water reactor. It is basically a Russian designed 1000 megawatt plant we are using. And this is a boiling water reactor where we have established in 1970s. And this is our core pressurized heavy water reactor. So here if you see, this is the core of the reactor. And from here, water will go to the steam generator. These are the steam generators. And from here it comes out. So this area is basically the nuclear island we call. And this area is anyway the turbine island, where it is quite conventional to any thermal plant. Another thing what is the next stage, second stage of a nuclear program, is fast breeder technology, which we use plutonium as a fuel. It is under a separate company known as Bhavini, BHAVINI, and we have already a fast breeder test reactor of very small capacity established, and one 500 megawatt electrical capacity prototype fast breeder reactor is under construction. It is in the final stage of commissioning, which we call. Maybe in another 1 or 2 years, this may become operational. So this is using metallic sodium as a coolant and using plutonium-239 as the fuel. So these are some pictures of this Bhavini reactor. Like core is like this, and you have a vessel here, and sodium pumps are also inside here. So here, if you see, this green is a thorium blanket what we are putting. Thorium and uranium-238 blanket will be put. Means rods will be put here. Somewhere here you will be putting. So what will happen? Inside we have plutonium-239, from where heat energy will come. And this thorium-232, they will absorb one neutron and it will become uranium-233. So uranium-233 is another fantastic thing which can be used as a fuel again. And uranium-238 will become again plutonium by absorbing again U-239. So plutonium-239 will be used again in the fast breeder, and uranium-233 which comes out of this can be used again further in the third stage program. So I was mentioning about the thoria or monazite sands available in our country. Lot of around what you call large deposit of monazite sand is available in our Kerala and southern part of the country, and it is abundant than uranium. That is one of the greatest things. And one of the greatest advantage of this thorium is if it is converted to uranium-233, and the actinides which come out, these are very less compared to this what you call conventional reactors which use to uranium-235. We have lot many actinides which is radioactive. The quantity of actinide which comes out of thorium reactor is very less. So this way, this will provide a miracle in due course of time. Of course, this time cannot be predicted because we have been working on this in a research mode only now. Also, we have not come out of this research mode. Maybe upon time, maybe another 10-15 years, we will be able to come out commercially within such a venture. So we in India follow a closed fuel cycle. So uranium mines and mills are there, and from there it is converted to uranium oxide, and it is converted into fuel. We have a NFC nuclear fuel complex, and this fuel is given to reactor, and from the reactor it goes to reprocessing plant, where you have plutonium produced again, which can be used in the fast breeder reactor, and reprocessed uranium also is there, which again is converted to uranium oxide, and it is again converted to fuel. So this way, most of the fuel is reprocessed and reused in the reactors and used in different stages. And finally, you have some what you call byproducts, obviously waste, which is very less. If you are using all the things inside, the radioactive waste will be very less. And there are lot many isotopes which come out of these reactors, which can be used in medicine, agriculture, and industry. Now, if you see the safety record, like Mr. Dominic was telling, one of the perception is unsafe. All nuclear reactors are unsafe. Or whether it is safe or unsafe, I don't want a nuclear reactor. That is a general perception. But you have to go by analysis and statistics, how safety is there. We have, basic theory in any nuclear plant is there are 3 C's. One is you have to control the reactivity and you have to cool the fuel always. And if at all, if some radioactive release is there, you have to contain the radioactivity. If these 3 are achieved in a scientific manner, any nuclear plant will be successful. So for controlling of reactivity, we have separate systems for power control. Okay, and that too during operating states and shutdown systems are there to quickly terminate the fission. I was mentioning about 2 additional backup systems, 2 shutdown systems are there. And they are 2 independent diabers. It is not that through one pipeline, both the things go. One pipeline will be here and one pipeline will be here. Assuming case, I'm just taking the layman's language. So we have 2 different routes will be there, divers will be there. And all these things are fail-safe design. Means if power supply goes, because of gravity, it falls down. This control of reactivity happens. And reliability targets for shutdown system design are also there. So we have developed so many new things like, in addition to the existing ones, there are self-powered neutron detectors, which is quite common. And this detects the neutron flux and acts independently. Then we have regional overpowered flux system. And there are different setbacks parameters based upon this flux, which is monitored. Neutron flux, what we monitor inside. Then the next C is cool the fuel, We have during normal power operation, there is nothing to worry about. It is for power generation. And it is required for shutdown condition. The one of the most critical areas in nuclear plant is during normal operation, nothing is there. But when it is shut down, the fuel has to be cooled always. That is a basic requirement. Heat removal from reactor core and also stored spent fuel. These are the 2 important parameters in any nuclear plant. And for this, we should have multiple systems for heat removal and that too through reliable power supplies. So we have, for this what we have is shutdown cooling system with capability to get involved in at a full system pressure and temperature. We have a diverse, if a normal shutdown happens, we have a separate cooling circuit which comes into picture. And with that, we have 2 different trains of emergency cooling system. And if these 2 are operating on electric power, and if this fails, we have one passive system which is not dependent upon any electric energy. And third is, I was mentioning earlier, how to contain a reactivity, how our containment got evolved. So overall, we do the proof testing of the containment also at a higher pressure once it is constructed. That way, all assurances are there that reactor is always safe. So we have standardized the design now, and multiple units like 7 gigawatt units will be set up in the near future. And we call it as a fleet mode of procurement, like standardized design will be adopted and standard 3D design we have adopted now. And we are emphasizing on re-engineering limited to site specific changes only. Means like you want to establish a plant here and you want to establish a plant some 200 kilometers away, the design will be same. In the sense, based upon site specific, some local changes has to be made. Like that we have standardized now. And bulk procurement mode we are going, and standard safety analysis, standard technical specification for plant operation, and all procurement is also standardized now. Now coming to future nuclear technology, this is one hot topic which has been going around, and it is very interesting. It is small modular reactor, and world over people are talking on this. They are rated between 10 to 300 megawatt, and it is suited for off-grid and remote locations. Like it need not be connected grid. Let us say you want to have you have an energy requirement for this town as 200 megawatt. You put a SMR here, and it will cater for this town. That's what they speak now. They, in the sense why I'm using that term, it has not been put in a commercial use so far, not much of a thing. Then modular means, why it is known as modular, they are factory assembled to reduce the construction time. This is the greatest advantage of this reactor. Like any reactor, any commercial reactor, whatever I have told, all these construction activities happen at site only. Here we have, it can be assembled in the factory and it can be delivered. The next is full passive systems are there. This is one of the greatest things, so that no human intervention is there. Then very small area is only is required, and they are based on presently they are based on pressurized water technology, but it is coming forward. Some sodium cooled, some high gas cooled, all these things are coming. Now there are two different technologies of SMRs which based upon literature is available. One is block type SMR, they call, you have to have a pump to cool this reactor core always. So this is a reactor pressure vessel and 4 pumps are welded onto this. And as a whole, this will be assembled in the factory and will be shifted to the construction site. And you have one more new thing known as integral SMR, where you have inside the whole vessel, you have the pumps. These are the two things. So all these things come from the factory and you have to simply fit over there. This is a new concept what is coming now. Another thing is micro reactors. I will touch upon that in the coming slides. So we have land-based water-cooled SMRs, that is pressurized water reactors. Then marine-based, like water-cooled. Then the same water-cooled SMR, marine-based, you have a ship or barge where you can stable the nearby beach or somewhere you can go there, and through that you can get electricity. Then third one is high-temperature gas-cooled reactors are also there. Then liquid metal-cooled fast. Metal cooled with sodium is mostly used, or sometimes lead also there. That also is there. Then molten salt reactors. Molten salt also is being used. And micro reactors, which are of the capacity of less than 10 megawatt. The technology, so far, PWR technology is only being primarily developed by most of the vendors. Then amongst the PWR based SMR designs, there are two variants. One is block type, which we have discussed, and another thing is an integral thing. And it's like this is having more prominence now other than integral. These both two are coming up. If you see world over, of course, this is an integral picture of an integral SMR. This is a see, one of the greatest advantage here is they require less frequent refueling. Refueling length is 3 to 6 years. Means in our pressurized heavy water reactors, what we use in India, every day we have to do refueling. Okay, it is on power refueling. And light water reactor, what we have is in an year average, or maybe in 1.5 years, you have to take the plant, you have to shut down the plant for around 1 to 1.5 months or 2 months, and you have to do the refueling. So that much plant will not be available. Whereas in an SMR, it is being claimed or it is being conceived that if you fill the fuel and you start producing, average refueling length is 3 to 6 years. So 300 megawatt without any interruption for 3 years continuously power. So it will be an attractive thing once it comes. And you have one emergency planning zone concept attached with any nuclear plant. We have 10-kilometer radius. You should have identified it is an emergency planning zone around a nuclear plant. And that is in case of any eventualities, you are supposed to evacuate those persons or something. In Fukushima also, lot many evacuation was done. But in SMR, it is being told that it is a walk-in reactor. There is no emergency planning zone. So you can put a reactor in an open area and remaining activities can go as business as usual in the outside area also. But SMR attractive, but this is the fact now. Like, 86% of the designs all over the world, it is still in the design phase. Like early stage is 6, different types of designs are there. And around 50% are in the conceptual design stage. And basic design stage is around 7%. And some are advanced is around 15%. So around 62 or more than 60 is still in design phase. And another 5% is in licensing phase. So if you see around 67% are still in paper only. Okay. And 2% have come up to construction, 2.8% have come to construction. And another 3 units, they are under operation. So we have only very few under in practicality. This is the reality of SMR now. So different types of reactors in SMRs are there. Maybe sometimes to the order of 450 also is their capacity. Now, different designs by Rolls-Royce is there, Westinghouse, then Korean country, Canto SMR is there, Canadian, then Russian design also is there, Chinese design also there, Argentina also have made some designs. So all these are the different types of SMR which are based on land. And these are marine based SMRs where you mount in a barge or you mount in a ship or something and start powering from there. These are also in the development stage, except for some of these SMRs which they have deployed already in some areas in the Russia or something. These are micro reactors, these are best suited for powering off-grid locations and also for industrial application, hydrogen production, etc., where you have less than 10, then 5 to 9, 2 to 4, and less than 2. This should be less than. So, in fact, small reactors which can be handled in a truck, and go to a suitable place and put it over there and start criticality and start what you call electricity production, energy production. This is again in a what you call conceptual stage only, except for 1 or 2 which would have come up. So both SMR and MR, if it is coming out of the paper and if it reaches a commercial application, then this may revolutionize the world. But as of now, this bit on a distant dream. In the sense, only 1 or 2 or 3 has come up, and whether we can call it as an SMR or how commercially viable it is, we have to see. So, with respect to safety, so these reactors, they carry zero risk to the public. This is one of the greatest advantages. And they are designed to, with a trademark, no impact on public domain. This is one of the greatest impacting statements what they do. And in SMRs, the size of reactor is very small. And hence this radioactive inventory also is very small. And hence this release at plant boundary never exceeds allowable dose limit under any circumstances during plant operation or even at shutdown. And no emergency planning or evacuation in the public domain. That is, it is walk-away safe reactor. This is one of the biggest jargons of this SMR, is no impact in public domain and it is a walk-away safe reactor. But as I mentioned earlier, that is still in conceptual or design or licensing stage, and how near we are in commercially exploiting this, we have to see. Now, one SMR which we have, which India have, is our indigenous 220 megawatt design is being pursued as an SMR for developing as a captive power plant. Our reactor of 220 megawatt design, even though in this there is a variance with respect to SMR with respect to fuel requirement. Here we have to do online fueling. Every day we have to refuel. But we are improving the safety aspects to reduce the emergency planning zone, like putting a container, then putting up hookup provisions, then we have some catalytic recombiner, and we have other containment system so that this can be deployed. Especially we are working towards replacing some captive power plants in India by putting this 220 megawatt PSWR, so that this, by the time SMR is conceived and developed, we have already a design of 220 megawatt reactor which can be put all over in our country. So if you see our, one of the reason why public acceptance is not there, other than accidents, you have radiations emanating from this plant. That's what they call. So this is the natural background. 2,400 microsievert per year. It comes from the natural background. Everywhere it will be there. Average. This is the world average. And we have one regulator, Atomic Energy Regulatory Board. They have prescribed a limit of 1,000 microsievert per year. And these are our plant sites where we measure at the boundary how much radioactivity is coming. So these are the values. This itself proves that our reactors are one of the safest reactors available. You compare this limit, radioactive regulatory limit is based upon IAA standards. And this natural background which come from, you don't have to do anything, it keeps on coming. And with respect to operation, we have continuously operated for around 3 years on reactor without any shutdown. And more than 1 year, in 365 days to 962 days, different plants have operated. And we have operated 41. Our plant operates more than 1 year. It is a common thing. There are some statutory requirements by which you have to take maintenance. Other than that, this PSWR once connected to grid, it will keep on operating. And IAEA has commended our responsible nuclear power. One of the basic requirements of any nuclear power country is that government should be responsible and committed for safe operation of the reactor. So recently, IAEA Director General Grossi had visited India, and he has complimented again and again our country's commitment for a safe operation of nuclear power. Then we have an advantage of what you call fuel cycle is fully closed. Then we have large human resource with us and multiple research reactor technologies. Then cost is one of the greatest advantage. So you have 1,900 kilowatt US dollar 1,900 per kilowatt. This is the what you call cost incurred in establishing this plant, because the cost of production in India is very less, as compared to other countries. And we have what you call this renovation maintenance. We do this emergency what you call en masse coolant channel replacement and en masse feeder replacement. We undertake every 30 years or something. That also is very less cost. Then now to reach the net zero, it is not that easy. It is like presently we are here, and CO2 emissions, it will peak sometime and it will come down. So if you leave business as usual, we keep on adding some plants, some coal plants are coming, some coal plants are retiring. So when we will reach net zero, it's not clear. But in Indian scenario, we have told 2070 is the net zero thing. And in that peaking may come, sometime around 2050. And in that, if we have a target of net zero of 65, year 65, peaking may come in this, whatever be the case, when peaking has to happen before the net zero is coming, because our country has to develop. In that, if you see the net zero of 2070, the area requirement, like if renewable is 95% and nuclear is 5%, nuclear can, how fast nuclear can come up has to be seen. The area requirement is this much, square kilometer, this much is required. And if renewable is 5% and nuclear is 95%, this much area only is required. So this is the greatest advantage when you have nuclear here. And if you have some fossil fuel here in between, and then also this area requirement is very large. And here you have nuclear 35, renewables 40, and fossil fuel 25. Area requirement is less than 1 lakh square kilometer. So nuclear has to play a significant role in terms of area. And if you think about the funding also, upon time, like if you want to have a net zero by this time, from today, total, if you see the investment cost as a whole, if you have nuclear 95%, 5.3 trillion US dollar has to be invested in India. Whereas if you have renewable 95, nuclear 5, $9.4 trillion is going to be the investment. So overall, if you increase the capacity of nuclear in the energy mix, the investment also will come down. This is a study done by IIT recently in India. Again, same slide. If you see the world scenario, presently we are here, 2021 or something like that. This is electricity. This is the share of electricity, and this blue is industry, and this red is transport, and these three are the major contributors as on today. And this has to be gradually reduced. Emissions has to be gradually reduced by 2050. Anyway, this is the commitment by developed countries, and Indian commitment is 2070. So there is a scale provided over here, which whether it is possible or see, we have to see. By 2025, nearly 50% of the electricity from low emission sources has to be there. And again, 8% emissions from cement production are captured and stored in 2030. And 60% of global car sales are electric by 2030. And no new sales of fossil fuel boilers by 2025. And by 2040, if you see, electricity accounts for 40% of industrial energy consumption also. Means electricity is coming here and it is merging with industry. Then 50% of existing buildings are retrofitted with zero carbon ready levels. Then here by 2045, if you see, no heavy truck sales, and 50% of heating are also met by heat pumps or something. So overall, it is a very easy and beautiful chart over here. But this requires a lot of funding. It will not happen without any huge investment. And who will invest and how the investment will come at as we see. If you see now, the investment in billion US dollars by 2050, it has to go up. By 2030, it has to go up to 2000 billion US dollar. And of course, by this time it would have stabilized. And in any decade, you have to invest heavily in the advanced economies. And in the developing countries, this will be touching 3000 billion US dollar for years to come. So this is the main debate of any COP meetings. What happens is, who will be who will be funding this new technologies and who will be funding for this clean technologies. So that is the main question everywhere. Technology is available, but one concentrated effort is required for meeting the targets. Now, to sum up, there is sustainable goals are being declared. SDGs, Sustainable Development Goals are there, which is declared by UN. 17 are there. In that, serial number 7 is affordable and clean energy. Once ensuring access to affordable and reliable sustainable modern energy for all is the central in achieving all 17 SDGs. Like one is poverty, another is zero hunger. All these things put together, this is the main thing. That's what I believe. Like if affordable is the main thing. Like if you invent some technology which I and you cannot purchase, then there is no point in having that. Maybe we can keep on talking about controlling CO2 emission, but costlier part will totally spoil the whole show. Now, in the world scenario, a cost-effective energy transition can be achieved with a combination of nuclear and renewable. Nuclear alone cannot serve the purpose, and renewable alone cannot serve the purpose. So it has to be an energy mix of both nuclear and renewable. And nuclear, we have the advantage of scalable, dispatchable, and low carbon source of electricity, and it contributes significantly to the energy supply and can do even more in a decarbonized system. Then we have sizable deployment of nuclear power. Sizable deployment, you should have large capacity plants also, and increases the chances of achieving net zero. So to sum up, nuclear, renewables, and the future technology of hydrogen also is coming up, which as on today is in the conceptual stage or slightly not that much commercialized. That only can help in an integrated low carbon energy systems. So that's all with me. So maybe I don't know whether I was able to communicate with you, or I was able to tell you, or I was able to convey what is the concern or what are the challenges about. Nuclear is one of the best option, what I believe, which can support in achieving the net carbon. That's all.
Great. That was fascinating. Thank you. It was really, really interesting. Time for some questions. If anybody's got any questions?
Yeah.
Rajesh, that was an absolutely outstanding presentation. Thank you very much. So I'm Tajinder Panasa, I'm the IOP's head of membership. You spoke about, things like nuclear being part of the energy mix. If you think about the energy mix, even at 1%, 2% is part of the energy mix on a technical level. What does the nuclear sector have to do to become more strident, to get the message out about, all the advantage or the advantage of more modular reactors being constructed and becoming online all over the world? Particularly not just in that sense, but also the fact that in the UK, we need more people studying physics at university, maybe doing masters in nuclear physics, nuclear science, and entering the nuclear industry. Because you spoke about people and manpower. Well, we need more of them if we end up with more modular reactors. So how can the nuclear sector become more forward-thinking, more strident, and to challenge the green lobby and to challenge everyone else who's also trying to, get a share of that pie in that sense of the energy mix?
Yeah. See, I can give the answer in 3 parts. Okay. First thing is, government and public has to work together so that public perception is there for nuclear. This is the baseline. If some group comes and start protest or start lobbying or something, then the attention of the government and public will move away from nuclear. So there should be first a public acceptability of nuclear. For having public acceptability, world over, how the plants are performing, that has to be told to each and every public. and what are the advantages of establishing a nuclear plant? That has to be given. Okay. For that, government level support has to be there necessary. Second is the toughest part. Fuel is available, uranium is available. Plenty of reserves are there everywhere. In not many countries, it's available. But infrastructure is not there for manufacturing of equipment. Earlier in 70s or 80s, 100 gigawatt of nuclear has been established in US, and after that there has been a long gap. Okay, there is no company as such is producing a mass scale nuclear power equipment. That infrastructure or the competency in industry also has come down. Now it is slightly picking up in our country and maybe in our neighboring countries also, China and all. Lot many companies have started, and that is why I've told you about 10 or 15 reactors ordering has been done for equipment, and that too multiple vendors are in place who are specialized in making this nuclear equipment. Nuclear equipment cannot be compared with respect to a normal equipment where you can do things very fast. Here you require passion and something. You have to have standard. You have to have high quality standards in this equipment. So as such, industry is, as of now, there is a small manpower, skilled manpower is not available. Skilled manpower in the industry is not available for making this nuclear equipment, which in our country is picking up now. Okay, globally, I don't know whether in your country or in other countries, whether this is there, because in developed countries, nuclear had saturated way back in last century rather, and after that, there is a gap. So the skilled manpower has gone away from this industry. So continuity of availability of nuclear manpower is required for production of equipment and construction of plant. This physics part or operating part can be made available, but you have to have input like in the sense of equipment and other things. That there is a large gap over there. This is the second part. And third part, initial funding, initial capital cost for any nuclear plant is high as compared to solar. Solar, you get a small solar panel, put it over here, and it may not cost you much. For a small pound you may get. But for a nuclear plant, you have to have a large investment in a nuclear plant. And anybody will hesitate whether that large investment is right or wrong. But upon time, if you construct a plant in average 5-6 years, and then consider break even, you will be able to give cheap power in a nuclear plant maybe after it is put into operation. So these are the three parts. First is government's commitment and public acceptance. It is very much essential. And for that, you have to have a lot of public awareness programs and other things, taking into account of the full statistics of the world. Second thing is non-availability of skilled manpower for getting this equipment and construction. That is a serious concern. So in our country, at least, lot many vendors are coming forward, and lot many dedicated manpower is there, so that is made available. And third is, one should not hesitate with respect to the capital investment, because the yield will be much larger. It is a clean energy, green energy, and it is that capacity factor I was mentioning, more than 90% it will work. Like our reactors have operated for 2 years continuously. So 2 years without interruption of power, if a power plant is giving a power, then it is fine. So I hope I was able to.
Yeah, thank you. Just a quick supplementary. All things you just described, they seem like really big barriers. I think my concern is there's such significant barriers that we may not achieve our net zero targets. And I think without nuclear, we're going to struggle. So we need nuclear online ASAP. But I just think whether the will is there amongst government and industry and the public perception to enable all these things to happen. But I'm with you. I agree. We need nuclear ASAP online.
That's true. Yeah.
What physically proportion you would suggest in like between renewables and new?
See, your question is good. One thing is that renewable and nuclear alone. Okay. If it is a mix, then you have to shut down all these fossil plants. Okay. But think of a scenario whether we have 60% in the present today's mix as fossil coming from fossil source. Whether all these things can be replaced by nuclear and renewables alone, that itself is a question mark now. There are advanced technologies which are coming, CCUS technologies, carbon capture, utilization, storage. So whatever CO2 emissions are there from these fossil waste plants, they are getting captured and they are being reused, or some mechanism is being developed so that fossil plants are also there in the industry. So nuclear can maybe in another 30 years or so, by 2050, it can supplement for 10% of the total energy needs of the country. It has to develop to that.
So would you then say like, for example, 90% is like wind, solar?
90% wind, solar, then CCUS systems you call, fossil fuels with carbon capture utilization systems. All these things has to put in place. And maybe after that, you have to develop hydrogen in a commercial grade. Like commercial usage of hydrogen also has to be explored. That research only is going on. We have to have hydrogen fuel cells, we call it, hydrogen fuel cells. It is not there, it's there only in lab scale or somewhere it has been explored, but it should come in an affordable scale. That also is required. Otherwise, we cannot keep on speaking about hydrogen. So all these things, once we talk about an affordable part also, that also is required. Like all these things, different forms of energy in the lab scale, and I have proved something if I tell, but unless it is useful for you in your purchasing capacity, whatever I do in the lab scale, it doesn't help out.
I'm just wondering if you have like 90% like solar, wind and all of that, and then the rest you say is like nuclear, but then like also, maybe I understood wrongly, but like you also said that then you want to have like big nuclear station.
Yeah.
But then like, if you still use the merit order in terms of the grids, then like the running costs, if you have to turn it on for like not the whole time, then it's really hard or like really expensive just like to turn it on, right? Like, because like if you have like full capacity all of the time, then it gets cheaper. But then if you have like most of the times renewables and then only like for a short amount of time, you have like the nuclear to like make up when the renewables are not enough.
No, it's the other way around actually.
So you would say like the renewables just if the nuclear is not enough. Because I don't get it then in combination with merit order, but maybe I'm not too much into the topic, so
maybe see renewables, capacity factor we call means in a year, how much time a renewable can give the desired. Let us say renewables give 100 megawatt. Assume a case, just arithmetics. We have a renewable plant here of 100 megawatt. So in a year, 100 megawatt continuously, whether it can give? No. Installed capacity is 100 megawatt. Okay, we have some 5 windmills of 5 megawatt, some 10 solar plants of some 10 megawatt or something. So adding up, it is 100 megawatt. Okay, assume a case. Now, if you continuously put in a year, you have only 30 megawatt which can be produced by this. It is because of wind will be available only for a shorter time, and sun, that solar also will not be available all the time. Night is not there, and some foggy days there, you don't have sufficient production. So 30 megawatt can only be produced if you have a 100 megawatt renewable energy plant. Okay, if you have a 100 megawatt nuclear plant, it will give 90 megawatt all the time. So if you want to have a requirement of 100 megawatt continuously in the region, you have to have at least a renewable plant of 100 megawatt and let us say a nuclear plant of 80 or 100 megawatt, so that those two combined can give 100 megawatt continuously.
Then wouldn't it be cheaper like to have like, for example, if you use renewables and storage systems, because then if you like, for example, if you combine like, say you have like Europe, or then you could have like lots of wind in the north and then lots of like solar in the south, and then if you have like really good grids overall Europe, and then like you can like maybe cover like the most of it, but then if you have like really sunny days or really windy days, you could use this to produce like hydrogen as a carbon as a kind of like waste product in a way, because then like if you have lots of solar and lots of sun and lots of wind, then it's free to produce hydrogen in a way. And wouldn't it be cheaper instead of like having like this really high fixed costs in the beginning of building a nuclear plant. And also because like uranium is like limited in like long term.
Yeah, I understood your question. See, nuclear plants can be phased out only if you have assured commercial viability of hydrogen. Okay, as of now, as of today, it's not there. Okay, hydrogen plant, we keep on speaking about hydrogen only. But let us say you have some 50 cars going here. How many are with hydrogen now? At least some 20% will be of electric vehicles here, and rest 80 will be fossil fuel fired only. So imagine all these 100% replacing with hydrogen fuel, and that hydrogen produced by a renewable energy. It's still a distant dream. That is first thing. Another thing is, this solar and renewable energy. They once it is connected to the grid, there is one technical thing also. It's basically an electrical engineering part, which I am also not proficient. For the power to have a movement, for a power electricity to have a harmonics, they call, you should have some base load stations also. Base load is some station which delivers continuous power. Renewable energy give intermittent power. In the daytime it is there, or wind, it is there when wind is there, or it's not there. Okay, for you to have a power connectivity from here to the northern part of the country, you should have a base load also transmitting across the grid. That base load can be given only through a hydel plant, or hydel, of course, no, to a large extent, nuclear plant definitely, and through a fossil fuel plant only, which continuously operates. So you require always a base load plant in the grid, and that if it is green, clean energy, nuclear is the only solution for that. Or we should have some CCU systems. Like you told, if hydrogen is coming out of lab scale, and if it is coming to a commercial scale, okay, then that will revolutionize the whole technology. But how fast it can be done, we have to see. And second thing is, like you have some small town in some remote area, and rather than taking energy and where you don't have much of a solar or wind or something, then there the best solution for clean energy is SMRs. Like you put a plant over there which pumps in another 200 megawatt or 300 megawatt electricity, and it caters for the whole town for a long period. So that will be one of the best form. Or if hydrogen comes again, of course, transportation is easy, and transportation of hydrogen, how cheap it works out, we have to see.
Can I ask, if I understood right, you're saying that fossil fuels will continue to be a part of the mix,
It has to be.
perhaps forever, do you think, or?
See, how the technology evolves, we have to see. Now the CCUS system, it is evolving. Carbon capture usage and storage and usage or something is there. So that carbon, whatever they are capturing, they are producing it to some. I'm not that specialist in that, but it is being used for producing so many byproducts, so that the CO2 emission is very minimum. Okay, and nuclear power, how fast it can expand. There are challenges, like he was asking. There are a lot of challenges in that, like non-availability of resources or manpower. All these challenges are there. So, and huge funding also is required as of now. So, an immediate replacement by nuclear power, it is not possible. But on long time, fossil fuel with controlled emissions, and nuclear power also producing sustainable and reliable, and with all renewables. This will be the whole global energy mix in a long time to come. And of course, supplemented by hydrogen, which can be used as a fuel in our cars or in all our vehicles. So transport sector, industry sector, and what you call power sector, all these things has to combine together to find out a clean mix.
More questions?
One final question for me. It's two parts. You've spoken about fission. What is your view on fusion? And secondly, you showed an image of those micro reactors. I think there was an image of a micro reactor on the back of a lorry. I mean, how viable is that going to be, having a micro reactor being traveling up and down the country, given public perception and other possible safety concerns or even terrorist concerns as such?
Yeah. Your first question was about fusion.
Yeah, what's your view on fusion?
Fusion, see, one of the SMR they call, I think in UK only I've read somewhere, some fusion based SMR is coming up. I'm not sure, I may be wrong also. But at least India as such is, I will not be able to say whether we are working or not. But a fusion reactor, we are presently concentrating on fission only. Okay. Fusion reactors, some years back it had come, but again, that what you call how technologically advanced or how technology challenge is that as of now, I'm not that aware. Okay.
Sure.
Second thing is micro reactors. See, you can have concepts or visions to any extent, like I have a what you call tab here and I have a small uranium pencil and I put it here, it will work for 1 year without charging. I can have an imagination like that. So micro reactors are conceived in that manner. Okay, like if you want to charge this building and you have small this thing and you charge it over there, so it is in the paper as of now. So how it can be translated into reality, time only will tell. Okay, there is nothing wrong in having a vision. Vision only will ultimately.
But do you think it's viable and practical?
See,
and
first,
possible.
safety has to be demonstrated. The foremost thing in any nuclear reactor is it should be proven safe. And once it is proven safe, then it will work out.
Thank you.
Okay. Any more questions? No? Well, thank you, Rajesh. That was
Thank you.
really fascinating. That's probably one of the best presentations on net zero
Thanks
stuff
for
I've seen
coming,
ever. Actually. So thank you again. People, there's some teas and coffees at the back if people want to run around and have a chat. Very happy to do so. Thank you.
Thank you.
Thank you.